let's look at part B. Find the x-coordinate of all global maxima and global minima of f of x on the interval negative infinity to 4. For each, write none if there are no global maxima or global minima. Okay, so let me just quickly recall that the critical points were x equals to 1 and 2. And let's see what we have to compare. So actually, before we even dive in, let me quickly mention that you cannot, so this is a common mistake. So let me mention that you cannot use a first or second derivative test for global max or min. Now, this is with a caveat. There are some pretty exceptional cases where you can use first or second derivative test to derive some global information, but this is really only in like, say, 1% of the case. So in almost any problem that you're going to encounter, if I tell you to find the global max or global min, you probably shouldn't be using first or second derivative test. You might get the wrong answer. In fact, if you try using it for this problem, you do get the wrong answer. So first or second derivative test, just so you remember, is for local. This is for local max and min. And this is very different concept than global max and min. For example, if I'm trying to find the function's global maximum on, say, this interval, so I picked this interval and you have a function that goes like this, so maybe this is your function, then if you look at this point, this is certainly a local maximum. Because when I really zoom in, and when I only look at points very close to it, so when I look locally, that's what I mean, then you see that this is the largest function value. But obviously the global maximum on this interval, the largest possible value of the function is happening here. So this is happening at the end point, in fact. So global maximum is here because and that's larger than the local maximum. The first or second derivative test can detect like local maximum, local minimum, but it might not be able to detect some subtlety like this one. So we cannot use first or second derivative test. So how do you find global max and min? Well, the first step of finding global max and min is find the critical points. And thankfully, in part A, we found them. So first step, we're done. And now here is the second step. The second step is to compare appropriate limit and values, or compare appropriate limits and function values to derive a conclusion. So this is very, very vague. So what do I exactly mean by this? Well, here's what we're going to do. We're going to compare a bunch of numbers. So we're going to compare, and the values that you're going to compare for sure are going to be critical points on the interval. So I guess this is something that actually should be pointed out. So if our interval happened to be, say, negative infinity, 0 instead of negative infinity, 4, then even if the critical points are x equals to 1 and 2, these are not in the interval in which we're trying to find the global maxima or minima. So you'll be throwing them out, and there will be no critical point to check. So we only care about critical points in the interval given to us, over which we're finding global max and min. So in our case, 1 and 2 are both in the interval, so we do care about them. And what we're going to do is we're going to look at the value of f of 1, and we're going to look at the value of f of 2. Now, you're not done. You also have to look at what's happening near the end points. So here, one end point is negative infinity, and since negative infinity, you're not treating it as a number, you can only approach it from our interpretation in this course. So we're going to take the limit as x approaches negative infinity of f of x. So you cannot plug in negative infinity is what I mean. So you should take the limit at negative infinity, and you also look at the right end point as well. So here 4 is being included. That's being indicated by the square bracket. We actually include 4 in the interval, so we just have to check f of 4. Now here, let me mention, if you had a negative infinity, 4 instead, so if you had this instead, then what you are going to take a look at is not f of 4, because you cannot plug in 4. If I gave you an open interval here, then you're not including 4, so we are not allowed to plug in f of 4. But what you can look at, and what you should look at, is limit as x approaches 4 from the left of f of x. The reason for this is because you have access to things like 3.9, 3.99, 3.999. All of those are in the interval. So you can actually approach 4 from values to the left, from things less than 4. So you should take a look at this instead. If I change the interval, to say 4, infinity, where I'm not including 4, then what you want to look at here is limit as x approaches 4 from the right of f of x, because now you have access to things like 4.1, 4.01, 4.001, so you can approach 4 from the right. So depending on what interval you have, the kind of things you're going to look at are different. So here, in our case, we have negative infinity, which has to be a limit at one endpoint, and we have 4 including 4, so we take a look at f of 4. So these are the 4 values we compare. So just to recap, we look at the critical points inside the interval, and you take a look at the endpoints, and we either write down the limit or the function value as appropriate. So that's the first step. And now let's actually do the comparison. So f of 1, so I guess we have to remember what our f of x is. So our f of 1, well, when x is 1, you're looking at this branch. When you plug in x equals to 1, you'll see that you get e to the 0 power, so which is 1. So you just get negative 2. So we get negative 2. Let's take a look at f of 2. What is f of 2? Well, 2 you plug it in here, so you get 8 minus 12 when you plug in 2, so you get negative 4. So you get negative 4 here. When I plug in 4, so let's go back to f of x. So when I plug in 4 here, you can do the calculation. You get 64 minus like 3 times 16, so 64 minus 48, which is 16. So you get these numbers. And finally, let's take a look at what's happening at the top. Well, you're approaching negative infinity. So since you're approaching negative infinity, you are only caring about things less than 1, obviously. So this is the function that you care about, negative 2 e to the 2x minus 2. So let me write that down. So you care about limit as x approaches negative infinity of negative 2 e to the 2x minus 2. And this can be confusing, but it's not too hard to analyze. So as x is approaching negative infinity, x is becoming like negative million, negative billion, negative trillion. I mean, it's some really large number. And as that's happening, what's happening? You're raising e to like negative 2 million, negative 2 billion, negative 2 trillion. So this is e to a very, very negative number. And if you know, like, for example, e to a very negative number, this is 1 over e to a very large number, right? And this is really large. So you're doing 1 divided by something very large. So that's approaching 0. So we know this thing inside, as you're approaching negative infinity, is approaching 0. Of course, you cannot plug in negative infinity directly because it's not a number. You have to make an argument like the one I just made. So you know this is 0. So now, once you have it, now you compare. And we are going to see which one's the largest one and which one's the smallest one. So here the largest one is 16. And 16 is not a limit. It's a function value. So you can actually get 16 is my point. By plugging in 4, you can actually get 16. So you know this is a global max happening at x equals to 4. So this is nice. What about the smallest? What about the smallest value here? Well, the smallest value is here, negative 4. And you can actually achieve it because when you plug in 2, you actually get negative 4. So you know this is global mean at x equals to 2. So let me actually say a bit more. What if this thing happened to be maximum? So instead of 0, let's say this was like 17. So let's say this was the largest one. Then even though this is the largest one, you actually cannot get 17 because it's only a limit, right? You're taking a limit, so it's not a function value. So you're approaching 17, but you might not actually get it. So if this was the largest one, then the conclusion should be no global max. So if this was 17, then you don't have a global maximum. I guess I can say another thing. So let's say we change the problem to negative infinity 4, where you do not include 4. So let's say this was an open parenthesis here. So in this case, what would have happened is that instead of f of 4 on the side, you would have limit as x approaches 4 from the left of f of x is 16. So now what's the conclusion? Well, we have the largest value here, but you don't actually get the largest value because it's not f of something. It's actually the limit being the largest. And if the limit is the largest, you're not actually getting 16, you're just approaching it. So in this case, the conclusion again would be no global max. So I guess in summary, if your largest value can only happen as a limit, then the conclusion is it's either no global maximum or no global minimum. But if your largest or smallest value can actually be achieved as a function value, then you know you have a maximum or minimum at that point. That summarizes a lot of things that can happen. I guess it's also possible that some of these values are the same. So if this also happened to be negative 4, then you say the global minimum is happening at x equals to 2 and also at x equals to 1. So that's another possibility. Anyway, I think we covered most of the cases, if not all. So the conclusion here is that you have a global maximum at x equals to 4, and let me erase this, global minimum at x equals to 2.